Okay, everyone. So as promised, I'm going to go through a couple of these examples that we had some trouble going through, covering in class. So if we start off with this couple of these examples, just going through a couple of key concepts. First, hopefully these are becoming concepts that you're more comfortable with, but here's the data acquisition and the TE. The data acquisition is done during the frequency encoding gradient here, and then the TE is from the middle of the RF pulse to the middle of the echo. So the TE is already labeled from this. And here's the TE. And then if we were to add the data acquisition here, again, this is going to happen during that frequency encoding period here. Now for this problem, back we're looking at what is the gradient amplitude we apply during our RF pulse that creates this frequency and position relationship that we're using a lot, where frequency is gamma bar. So during the frequency during the slice selection gradient is gamma bar, is the gradient amplitude, and then the position. So we can use this relationship to say, if you want to say, we have, say Z is 0 here. If you want to shift it up to some location, and let's call this little delta F, or getting one step ahead here, little delta Z. Then to make this shift here, all we have to do is apply a frequency shift of our RF pulse of little delta F that is, we're just plugging into, we're just trying to get to this location, delta Z here, which maps to this location, delta F, and just can simply plug in our relationship there for frequency versus position. Okay, and then this example is very similar to some of those in the lecture notes, where I'm just trying to make it clear when we're acquiring, say, slice 1, and then this is just a little extended example here where we have for spin echo. So normally we would fill in the data for slice 1 with our certain phase encoding gradient step that we need. We go ahead here, fill the same thing for slice 2, and continue on here, fill in, let's say, this first line for slice 3, and then we'd step to, there'd be a, say, a smaller phase encoding gradient. We'd fill in another line back for slice 1, and so forth. Okay, and also, and here's this concept of active time and dead time. The active time is the time required for all the pulses to acquire the data for a single slice. And then it's this dead time in which we can acquire, we can interleave, we can acquire our other slices. Okay, this example we went through in class, but really, so this is, multi-slice interleaving, and really this technique, if you look at the contrast curves, it's good for long TR, so that means it's going to be good for T2 weighted and proton density weighted images. Okay, so I just wanted to review here the concept of aliasing and where, if we're going to have aliasing, where is it going to occur? And we can actually do this for an example. No, backwards here. Let's say it's for an object that's kind of like the imaging example where the nose was wrapped around, where the object is offset somewhat. And some guess at what the signal is here. Now, if we take this sample that some interval, recall this is our delta TS, that we're going to get this repetition of the object at 1 over the delta TS intervals. And actually, interestingly, when we have this shifted object, recall what happens when we do the discrete Fourier transform is the only region that we see here is this middle 1 over delta TS. So we'll get an image that would look like this, where we would see aliasing, although aliasing that is not necessarily destructive, right? It's not overlapping with another signal. Okay, but you want to remember that the signal is kind of wrapping around to the opposite side here. And I want to go through this same type of example and see what would happen actually with if we do anti-aliasing. So again, some guess is the signal curve. And now let's insert as this middle step is that we're going to send this through some low pass filter, or we'll say, and we'll call it an anti-aliasing filter. And, smooth out this drawing. And what you can think of the anti-aliasing filter is doing in frequency space is multiplying by some rectangular function of some, and so this is the frequency axis. This is our filter, sometimes notated with like a capital H. Would be a standard signal processing notation for this. And it has some bandwidth here. And in this case of this offset object, it'll do something interesting. It'll actually cut off the edge of the object potentially. Okay. So then when we go to sample this object, and if we choose our sampling bandwidth or our sampling rate, such that we matched our anti-aliasing filter, chosen the widths here to be the same. So if we're doing the anti-aliasing filter, we're going to match it to the sampling rate. Then we have this region over which the discrete transform is defined, and we're going to see this object that's been actually cut off outside of this region. All right, and if we wanted to, we can actually we could apply some shift or something and move the object around here too if we wanted to. All right, but this is another example of going through these aliasing pictures, where remembering that now we're going to have this when we do our data sampling, we're going to have a sampling rate or a sampling time requirement called the Nyquist criteria that's going to ensure that we don't get aliasing, or when we can, we may be applying an anti-aliasing filter to prevent that from happening.